Hello everyone, can you see my screen? Anyone? Is my screen is visible and I am clearly audible?
Yeah, sir.
Okay, thank you. So I welcome you all again to the introduction session on experimental physics 1, which is being for course code NOC23-ph37, which is being floated this semester by NPTEL. Myself, Vivekananda Nayak, I am a PhD research scholar at Department of Energy Science and Engineering, IIT Delhi. So let's start today's introduction session. So today we will discuss first about a few experiments and then we will solve the problems related to those experiments. So first we will discuss about how to determine the coefficient of thermal conductivity of a bad conductor. Now, what is thermal conductivity? Now, thermal conductivity refers to the ability of a given material to conduct or transfer heat. It is generally denoted by the symbol K, or also lambda can be used. It's the reciprocal of this quantity known as thermal resistivity. Like we know, for in different materials, there are different type. There are coefficients of thermal conductivity. Thermal conductivity means how easily or how it basically it represents the ability of that medium. Suppose we are considering air, and we know air is a very good thermal insulator. That's why uh, generally the houses are made like two roofs are made and there in between the air is trapped so that heat will not transfer from the top roof to the second layer like this. So also there are electrical conductivity like that. So if you talk about electrical conductivity is very much similar to that of the thermal conductivity nature. But so we can say that suppose in case of electrical conductivity, current I flows due to a pressure difference of, due to a voltage difference and across a resistance. So when there is a voltage difference, current flows in the circuit. Similarly, we can write it as I is equals to sigma B2 minus B1 divided by L into A. So basically, I request everyone to mute themselves. So because we know R is equals to rho L by A. So R is equals to rho L by A. So rho is resistivity. So 1 by rho will, so 1 by R will be A sigma by L, where sigma is the conductivity. So when we compare it to the transfer of heat, so we can say that heat, suppose this is a case where this T2 is the temperature of of a hot body and T1 is temperature of a cold body. So due to this temperature gradient, heat flows between this region. So suppose this is the cross-sectional area A through which heat flows. So we can write the total amount of heat Q transferred will be directly proportional to the cross-sectional area, because more is the cross-sectional area, more heat will be flowing from this hot body to cold body. And also this rate of flow of heat is directly proportional to the temperature difference, that is T2 minus T1. If the temperature difference is more, then the rate of flow of that will be more, and also it is inversely proportional to the distance, this distance D. So if we uh, write it, so it will be Q is equals to K A T2 minus T1 divided by D. So this K is coefficient of thermal conductivity. We call it at kappa, or we can also represent it as lambda. So this K is the coefficient of thermal conductivity and its reciprocal known as thermal resistivity. So during the lectures, you must have seen how the experiment is formed. Here, the experiment is formed to measure the thermal conductivity of an insulator or of a bad conductor. So there is a rubber of some sort of thickness, and that is placed in between two bodies. One is hot body, another is cold body. So we are measuring the thermal conductivity of that medium, that is the rubber. So talking about the next experiment is determination of electrical equivalent of heat. So we know there are different forms of energy. So there are mechanical energy, electrical energy. So similarly, there is heat energy. However, if you talk about heat energy, it is typically measured in quantities that are separately defined from the laws of mechanics or electrical magnetism. Like in case of um, laws of motion, there are different types of laws and there are different types of energy, mechanical energy, and in case of electrical energy, there are different types of formulations which are and these are governed by those formulations. However, when you talk about heat is similarly another form of energy, but its formulation is somewhat different from those you measured or those considered for electricity, magnetism, or in case of mechanics. So, first, Sir James Joule studied the equivalence of these two forms of energy and found that there was a constant of proportionality between them, and this constant is therefore known as Joule equivalent of heat or electrical equivalent of heat. That is, like heat is a form of energy. Also, there are other form of energy. So when we convert some other form of energy to heat energy, the ratio of these two is constant. That is known as Joule equivalent of heat. So Joule equivalent of heat is basically the amount of mechanical or electrical energy contained in a unit of heat energy. Also, we can say that the ratio of work done to the corresponding heat generated is always constant. So this constant is known as, this is Joule equivalent of heat. Joule equivalent of heat. That is, if we are doing some work means energy. So if we are doing some work, the heat generated gives it is a ratio, and the ratio is constant, and this constant value is called as J, or Joule equivalent of heat. So we know the unit of J is Joule per calorie, and we all know 1 calorie is equal to 4.2 Joule. So in the experiment that were performed in the lab, what was done in that experiment? In that experiment, the electrical work is converted into equivalent heat in the experiment. So how the electrical work is formed, we know if current is flowing, V is right proportional to I, so V equals to IR. And when current flows to resistance, then there is a heating which is called as I square RT. This is called as Joule heating, is not it? So if you write in terms of power, we know power is equals to VI or V. So V is equals to IR. So similarly, it will be I square R. So this V. So if you pass some current through a like this, if you can clearly see, this is a power supply of 0 to 6 volt, and an ammeter is connected in series, and there is a voltmeter to measure the voltage drop across these two immersion heater. So this immersion heater, when the current passes through this immersion heater, due to the resistance of that immersion heater, there will be heating of the water inside it, and due to the heating of the water, the temperature of the water rises, and that temperature is measured by the help of the thermometer. So we can see, if so we can say that we know power is equal to energy per unit time. So we can write total energy or heat energy Q will be P delta T, where T is the time taken. Or now this is the equivalent of electrical energy. Electrical energy. Now this electrical energy is converted into heat energy. So this heat energy gives rise to increase in temperature of this water and the calorimeter. This water plus here this is the calorimeter cup. So this water and the cup. So if you apply the principle of if you apply the principle of calorimeter, that is total heat lost by the total heat supplied by the immersion heater is utilized to heating the water and the jar. So in that case, the total heat energy will be how much? The total heat energy will be MC. We know the heat absorbed or heat radiated is written in terms of mathematical formula, which is MC delta T. So we can write here MC and delta T is the change in temperature. Here, I think I should make it as small t, because here it is time, where capital T means this is temperature. So there is water and there is this calorimeter. So we can say that it will be MW CW delta T plus M calorimeter, C calorimeter and delta T. So this is H, and we know Q is P delta T. So from these, so when we are supplying current through the immersion rod, then we can calculate power, and for a particular time we can calculate the energy supplied, and then from the formula of the change in heat or change in temperature, we can calculate the heat supplied to the calorimeter and the water. So from that relation, we can calculate J is equals to Q divided by H. So it will come around 4.182 joule per calorie. So this is the experiment which is used to measure the electrical equivalent or joule equivalent of heat. And there is another experiment which for determination of specific heat of the given solid metals using Dulong and Petit's law. So basically, what is Dulong and Petit's law? According to Dulong and Petit's law, the product of specific heat and atomic mass of an element is always constant, and it is more or less constant for all solid elements, or either it is metal, non-metal, other. So basically, Dulong-Petit's law gives an idea about the molar specific heat, because we know specific heat is defined as the amount of heat required to increase the temperature of 1 gram of substance through 1 degree Celsius, but molar specific heat is the amount of heat required to increase the temperature of 1 gram mole of a particular substance to 1 degree Celsius. So this product of mass into specific heat is called as molar specific heat or heat capacity, and this heat capacity is nearly equal to 3R for all the solid elements. So here R is universal gas constant, whose value is 8.314 meter square kg divided by second square Kelvin into mole. So this is universal gas constant. And now, but actually, Dulong-Petit's law is not valid under all conditions, but at higher temperature, as you can see from this graph, this is the variation of this Cv. Cv is nothing but specific heat at constant volume. As you can see, Cv is not 3R at all temperature. However, as the temperature increases, all these metals or all these solid materials approach that constant value of 3R. So basically, we can also, if you talk about law of equipartition of energy, we know according to the law of equipartition of energy, the energy per particle per degree of freedom is given by half kT. So energy, if you write, so energy will be half kT per particle and per degree of freedom, per particle and per degree of freedom. Now, if you talk about vibrations, then vibration has 2 degree of freedom. So in that case, so if you consider about this vibrational energy, then it will be 2 into half kT, or it is kT, because due to vibration there are 2 degrees of freedoms. So, and we consider in case of solids, we consider each atom or each molecule, the substance to be made up of a number of oscillators. So in that case, the corresponding energy of each oscillator is given by kT. So now in 3-dimensional case, for n particle, we can write the total energy will be 3n kT. So we know Cv is equals to del E by del T. So it will be 3nk, or we can write it as 3R. So this is basically a classical law which states that the specific heat of the substance or heat capacity of 1 gram mole of any substance is 3R at all temperatures. So however, in the experiment, we have to calculate the Cv, because in the previous experiment also, here we are MC. So here MC was present in the formula. So in this experiment also, we can use the principle of this calorimeter, that is heat lost equal to heat gain, and from this we can calculate the specific heat of the material which we are testing. Then another experiment which we have discussed is determination of calibration curve of a given, that is type K chromel alumel thermocouple, and hence determination of Seebeck coefficient. So during the initial days of the international session, we had discussed about thermocouple, how in the thermocouple, the temperature difference between between the junction of two dissimilar metals give rise to voltage along the two terminals. And so there are so this effect basically is called as thermoelectric effect, and thermoelectric effect is the direct conversion of temperature difference to electric voltage and vice versa, and which is achieved with the help of a thermocouple. So this temperature difference directly give rise to electric voltage, or the voltage difference give rise to temperature difference, and this is achieved with the help of a thermocouple. And the thermocouple is thermoelectric device is mainly used, and that creates a voltage when there is different temperature on each side. Also, I have told you that when there is a difference in voltage, so there will be movement of electrons between the two terminals, and due to the movement of electrons, one terminal gets heated up and another terminal gets cooled down. So there is a temperature difference that result in the change in temperature of the two terminals. And the thermoelectric effect, which is the conversion of electrical voltage to heat energy, or temperature difference gives rise to electric voltage, can be defined in terms of three effects. One is Seebeck effect, another is Peltier effect, another is Thomson effect. So what is Seebeck effect? Seebeck effect is conversion of heat directly into electricity, and the exact reverse is called as this Peltier effect, which is conversion of electricity into heating or cooling. That is, when we provide a potential difference, then there will be heating or cooling depending upon the terminals uh, um, uh, terminals about which we are giving the potential, or we are applying the voltage. And there is another effect which is called Thomson effect, and Thomson it is that there is a temperature gradient when current flows through a single wire. So when current flows, generally the effect is more. These three effects are more or less same, because current flows when there is a potential gradient or potential difference. So all these effects are more or less same. So now talking more about Seebeck effect. The Seebeck effect is the electromotive force that develops across 2 points of an electrically conducting material when there is temperature difference between them. So what is Seebeck effect? Now, if you remember, we also discussed these things, but let me explain you once again. So when there are junctions of DC metals and they are kept at two different temperatures. So when they are kept at two different temperatures, there is a electromotive force that is developed along the two terminals, and that effect is called as Seebeck effect. And the EMF which is developed is called as Seebeck EMF or thermo EMF or thermoelectric EMF. So this ratio, the ratio between the EMF developed due to the temperature difference is called as Seebeck coefficient. So Seebeck coefficient is defined as the ratio of developed EMF to the temperature difference. So you can see this is the formula for Seebeck effect. S is equals to minus del P by del T, and the unit is microvolts per degree Celsius. And it is obvious because the voltage developed will be very small when you compare it in terms of the change in temperature. So a thermocouple measures the difference in potential across this hot and cold end, and this potential difference is proportional to the temperature difference between the two ends. So from this formula, you can easily see S is so S is given by minus of del V by del T. So if S is positive, then the end with higher T has a lower V, because the coefficient is defined in such a way that there is a negative sign in the coefficient. So the end with higher temperature will be having lower voltage. So the for higher temperature, the end which has temperature higher than the other end will be having the voltage difference will be so the voltage developed across that hot end will be lower than that of the cold end, and the EMF developed can be represented in terms of this temperature as a function of temperature, which is E equals to AT plus BT square plus CTQ, like that, and T equals to TP minus T reference. So these are constants A, B, and C are basically depend upon the type of thermocouple, and these constants can be determined by calibrating the thermocouple. So in the experiment is performed to draw the calibration curve of the thermocouple, that is the potential developed, and in x-axis it was the change in other temperature difference, and the slope gives the Seebeck coefficient. And the next experiment is theory and demonstration of platinum resistance thermometer. So platinum resistance thermometer is basically the resistance thermometer that work by changing resistance and changing temperature in a repeatable manner, because we know, like linear expansion also, there is temperature dependence of the resistance, which is given by, like in linear expansion we were saying alpha is equals to LT minus L0 by L0 into T. Sorry, this is T. T is temperature difference. Similarly, in case of resistance also, there is a temperature coefficient of resistance, which is given by RT minus R0 divided by R0 into T. So the resistance is also a function of temperature, because due to change in temperature, there is more movement of electrons or the charge carriers inside metals or semiconductors or non-metals, and due to this there is change in resistance. So if you talk about metals, with increase in temperature, the resistance increases. But in case of semiconductors, with increase in temperature, the resistance decreases. So metals have negative coefficient of resistance, negative temperature coefficient of resistance, while semiconductors have positive temperature coefficient of resistance. So can anyone tell me why in case of metals, as we increase the temperature, the resistance increases, but in case of semiconductor, this is exactly opposite or different? Yes, can anyone tell me? Yes, anyone? Because I told you that when we increase temperature in case of a metal, the resistance of that metal increase, resistance of that metal increases. But in case of semiconductors or in case of insulators, the resistance decreases. Why this is so? Any idea? Can anyone tell me? So can anyone tell me what do we mean by resistance? So we know so when we talk about resistance is the resistance is the obstruction of the flow of current. So suppose this is an cross-sectional area and electrons are flowing. So electrons are flowing over a cross-sectional area of A and through a length L. So if you talk about resistance, R is equals to rho L by A. So why the formula is so? Because this quantity is called as resistivity, which depends upon the material, and this is L is the length of the wire and A is the area cross section. So if you see here, if the length is more, then first we need to think about how the resistance arises. So when electron move inside an electric wire due to potential difference, so since they are moving, they will collide with each other, and due to those collisions, there is some opposition to the motion of the electrons from one side to another side. So you can clearly see from this relation why the resistance is proportional to L, because as the electrons travel large distance, then the probability of collisions are more, so the resistance will increase. So R is right proportional to L. Similarly, if you talk about area cross section, since electrons are moving in a cross sectional area and moving perpendicular to it, if the area cross section will be more, then more electrons will be moving, so the resistance will be less. So in that case, we are writing R is inversely proportional to A. So this is the case. But what happens in case of metals and in case of semiconductors? In case of metals, the number of free electrons are many. So free electron is, there are a large number of free electrons in a metal. Those conduct electricity. So metals have very much less resistance when compared to semiconductors or insulators or electrical insulators. So when you increase the temperature of a particular metal, so due to this increase in energy, the electron will collide each other more frequently. Like if there is a room and in that room there are 50 students. So when the 50 students try to go outside to the room through a single door, then there will be more collisions than in case where there are only 5 or 10 students. So in that case, we know when you increase the temperature, then there is thermal agitation, and due to thermal agitation, there is collision or vibration of the particles. So due to presence of a large number of particles, they collide more frequently with each other, and due to which the resistance increases. So in case of metal, so in case of metal, so in case of metal, if temperature increases, this resistance increases. So due to increasing temperature, there will be more frequent collisions between the charge carriers. However, in case of semiconductors or insulators, there are a very few electrons present to conduct electricity, and so they have less conductivity in compared to metal. But when the temperature increases, due to the breaking of the bonds present in the particular substance, there will be increase in the number of charge carriers, due to which there will be less resistance. So in semiconductor, with increasing temperature, the resistance decreases. So this is the case. So basically, this So as we discussed, the resistance changes as a function of temperature. Now, how the resistance thermometer is made? They are made from a length of platinum that is either wrapped around a ceramic or a glass core. Now, you can see from this figure, there is a glass coating and there is a core, ceramic core, and there is a platinum wire wounded. And in this case, the similar setup, there is a hollow pipe of insulating material. It can be ceramic or mica. Then this terminal is connected to a Wheatstone bridge or Carrick-Foster bridge. Basically, Wheatstone bridge and Carrick-Foster bridge are more or less same, but there are a modified. Wheatstone bridge is the more basic one. The Carrick-Foster bridge is a modified one. So, what is the Carrick-Foster bridge? So you must have performed the experiment in your. Um, so you must have seen the experimental lectures. So in Carrick-Foster bridge, this is a circuit which is used to measure the value of the medium resistance or to measure the small difference between the two large resistance. Because we know in case of Wheatstone bridge, when the bridge is balanced, the Wheatstone bridge is like that. So this is the Wheatstone bridge, and there is a galvanometer in between. So this is P, Q, R, S. So when P by Q is equals to R by S, so then this is called as balance condition, and then there is no current. That is, this Ig, current passing through the galvanometer, becomes zero. But if the bridge is not balanced, so there will be a flow of current, and this principle is used to measure the difference in resistance or to measure the resistance of a, so to measure medium resistance values or to measure the difference between the resistance of two large resistances. So it was invented by Carrick-Foster as a, and it is a variant of Wheatstone bridge. So this is the balance constant of Wheatstone bridge. So now how this is formed? So in case of X, we first place a known resistance. So in case of X, we first uh, place a unknown resistance, and in case of Y, in the position of Y, we place a known resistance. So it will be P by X is equal to Q by Y. So in this case, if P by X is equal to Q by Y, so there will be no current in this galvanometer, and we call it as the balance bridge. So when you adjust the contact D along the bridge with respect to EF, so this is a wire. So when you adjust this contact, so that there is a null in the galvanometer, that is no current will flow in the galvanometer. So this position is called as L1. So similarly, we change the position of Y and X. So in that case, there will be another position where the null point per percentage is sigma. Then the resistance difference can be calculated. The resistance difference is x minus y equal to sigma L2 minus L1. So in this way, the Carrick-Foster bridge is used to measure the unknown resistance or to measure the, like, if the two resistance are unknown, then there will be, if the two resistance are unknown, then we can measure the difference in the resistance. If one is known, then we can measure the second resistance, so, whose value is unknown. So now these are the experiments which were discussed in the last week. Experiments. Now the first question says the amount of heat flowing through a body by conduction is directly proportional to the surface area of the body, directly proportional to the temperature difference on the two faces of the body, inversely proportional to the thickness of the body, or all of the above. So this is a very easy question. Can anyone tell me what will be the correct option in this case? Yes. So as we had already discussed, the amount of heat flowing Q is right proportional to the cross-sectional area. Suppose these are the two faces. This is A and this is D. This is T1, this is T2. When T2 is greater than T1, then heat will flow this way. So this amount of heat flowing is direct proportional to A, is direct proportional to the temperature difference, and is inversely proportional to the distance between the two faces. So the first option says direct proportional to the surface area of the body, which is true. Direct proportional to the temperature difference on the two faces of the body, which is again true. Inversely proportional to the thickness of the body, which is again true. So the correct option will be all of the above, because all of these above three conditions are satisfied. Is it clear to all of you? Okay, so next question. The question says one end of a 50 centimeter long copper rod with a diameter of 4 centimeter is kept at 475 degrees Celsius, and the other is immersed in water at 25 degrees Celsius. Calculate the heat conduction rate along the rod. The thermal conductivity of copper is 380 watt per meter into Kelvin. So, what does the question says? The question says there is a 50 centimeter long copper rod and the diameter is 4 centimeter. So one end of the copper rod is placed at a temperature of 475 degrees Celsius and the other is immersed in water, which is at 25 degrees Celsius. So for a copper rod, there is a temperature gradient between its two ends, and due to this difference in temperature, there will be conduction of heat. So we need to calculate the heat conduction rate, and also the thermal conductivity of the copper is given. So we need to find out what is the conduction rate of the heat that will be flowing from one end to the other. That is the end at 475 degrees Celsius to the end at 25 degrees Celsius. So I'll give you a few minutes to solve this. So please try to solve it and tell me what will be the correct option. Yes, anyone solved it? So let's then solve this. So from the formula we know the heat conduction rate Q is equals to K, this temperature difference T2 minus T1 into cross section area A divided by D. So D is here, length of the rod, A is the cross-sectional area, K is the thermal conductivity, and T2 minus T1 is the temperature difference between the two ends. So in the problem it is given this K, we have K 380 watt per meter into Kelvin. This D is 50 centimeter or 0.5 meter. Area cross section A will be pi into 0.04 square, and T2 minus T1 is 475 minus 25, which is 450 degree Celsius. So this 450 degree Celsius will be again for then this is the temperature difference, so it will be Kelvin again, because 470, if you add in both cases 273, so it will be same. The difference will be same. So 450 will be the temperature difference. So Q will be 380 into 3.142 into 4 diameter 4 centimeter means 0.04 square into 450 divided by 0.5. So if you calculate it, it will come 29.5 watt. So this is the answer, and the correct option is 429.5 watt. So we know the formula is the rate of heat conduction is directly proportional to the temperature difference, cross-sectional area, and is inversely proportional to the distance between the two ends, and the proportionality constant is the thermal conductivity. We have all the values in the question. So when we put all these values, we need to calculate only the cross-sectional area, and all other things are given. So when you calculate the heat flow rate is 429.5 watt. Is it clear to all of you?
Sir, in this case, area diameter is given as 4 centimeters, so it will be pi into 0.02 square, right?
Sorry, yes. So it will be 0.04 by 2. Sorry, it's right. So it is 0.04 by 2. So thanks for correcting me. So the pi, so area is pi r square. So it will be pi d square by 4 or 0.04 by 2 square. Okay, so let's. So is there any doubt in the previous question, or we should proceed to this next question? Okay, so the question says a resistance thermometer reads are equal to 20 ohm, 25 ohm, and 40 ohm at the ice point, the steam point, and the temperature 20 to 50 degree respectively. So assuming that the resistance varies with temperature as RT equals to R0 into 1 plus alpha T plus beta T square, find the value of alpha and beta. So as we are discussing that the resistance of the substance varies and it depends upon temperature. So this resistance at a particular temperature T is given as R0 1 plus alpha T plus beta T square. So we have three cases. One is 20 ohm. So 20 ohm corresponds to 0 degree Celsius. 25 ohm corresponds to 100 degrees Celsius, and 250 and 40 ohm is at 250 degrees Celsius. So this is how the resistance is varying with respect to temperature. So this is the formula, or this is the relation between temperature and the variation of resistance. So we need to find out these two variables alpha and beta. So these are the options. So how to do this? Because we know at 0 means at 0 degree Celsius. So we know at 0 is 20 ohm, and we have two other values 25 ohm and 40 ohm. So if you put the values in the equation, T is 100 degrees Celsius and R is 25 ohm, then there will be one equation coming out of it. And from this same relation, when we put 250 degrees Celsius and the resistance is 40 ohm, there will be another equation. So there are two equations and there are two unknowns also, alpha and beta. So by solving these two equations, we can easily calculate alpha and beta. So I request everyone to try it and we will discuss it. So I request everyone to solve it and tell me what will be the correct option in this case. I already explained you how to calculate it. So you just put the values of the resistance and temperature. There will be two equations and the unknowns are also two. So when you solve the two equations, you will find the value of alpha and the value of beta. So anyone tried? Yes. Anyone solved it? So there will be two equations. But we know R0 is 20 ohm. So what are the two equations? So first case 25 equals to 20 into 1 plus alpha into 100 plus beta into 100 square. So it will give, this is 5 equals to 4 into 1 plus 100 alpha plus beta. Then the second equation is 40 equals to 20 into 1 plus alpha into 250 plus beta into 250 square. So it will be 2 equals to 1 plus 250 alpha plus 625 beta. So these are the two equations. So when you solve these two equations, you will find beta is 10 to the power minus 5 and alpha is 1.5 into 10 to the power minus 3. So what we can do, we can solve. So can you solve it now or I need to solve it completely? I request you to please respond, because if you can't solve these two equations, then I will be solving it now. Or if you can, then I will proceed towards the next question. Okay, so I think you can solve it. So let's consider the next question. The question says the resistance of a ball filament is 100 ohm and at a temperature of 100 degrees Celsius. If its temperature coefficient, if the temperature coefficient of resistance is 0.005 per degree Celsius, then the resistance will become 200 ohm at a temperature of option A 200 degrees Celsius, B is 300 degrees Celsius, C is 400 degree or 500 degrees Celsius. So the formula is same. You need to only consider alpha, because there is the, so you can, the unit of alpha and beta are different. Like in the previous case, the unit of alpha is per degree Celsius, but the unit of beta is per degree Celsius square, because the formula is in this way. So since here it is given alpha 0.005 per degree Celsius, so it is alpha only, because in case of beta it is 1 by degree Celsius square. So alpha is given, so you need to only use the formula at t is equal to r0 1 plus alpha t. So you can use this formula in order to calculate the value of alpha. In order to calculate the value of temperature T, where the resistance will be 200 ohm. So it is pretty much similar to the previous question. So I will give you a few minutes. So please try it and tell me what is the correct answer. So let's calculate. Anyone calculated? Let's calculate it because we know RT equal to R0 1 plus alpha T. So we know it's given 200 ohm and it is 100 ohm. So 200 equal to 100 1 plus alpha and T is here. We need to calculate. So it is 1 plus alpha T equals to 2. So alpha T equal to 1 or T equal to 1 by alpha or 1 by 0.005. That is 1000 by 5, that is 200. So this is the 200 when you have considered R0 is 100 degrees Celsius, because we have considered R0 is initial value. So at initial temperature of 100 degrees Celsius, the resistance is 100 ohm. So when the resistance become 200 ohm, so the increase in temperature is 200 degrees Celsius. So the actual value of the temperature will be 200 plus 100. So the final temperature at which the resistance is 200 ohm will be. So the final temperature will be 200 plus 100 equal to 300 degrees Celsius. So the correct option is option B. Then the question says, which of the following graph represents the variation of thermo EMF with temperature of two different metals which are joined end to end. One end of the metal is kept at a constant temperature while the other end is heated at a very high temperature. So can anyone tell me what will be the correct option? Yes. So the question says which graph represents the variation of thermo EMF with temperature. So if you remember the thermo EMF, so this is the general expression of thermo EMF. It is E equals to AT plus BT square plus CT cube. So the thermo EMF is given by E is equals to AT plus BT square. So now actually A is positive but B is negative in case of certain substances. So if V is negative, If A is positive, we know E is right proportional to T. So the graph will be straight line. But since there is another term T square term, and this T square is negative, so the value will, as we go after certain time, for larger T, the value will decrease and the value will be like this. So the correct option is option D. Because here it is given while the other end is heated at a very high temperature. So when we go towards higher temperature, then this T square will be dominant. And since this B is negative, so the value will decrease. So at higher temperature, the relation is like given in option D. Then the next question is a piece of copper of mass 200 gram and a specific heat a piece of copper of mass 200 gram and specific heat of 0.1 calorie per gram per degree Celsius is heated to 100 degrees Celsius and then quickly put into 120 gram of oil at 20 degrees Celsius contained in a copper calorimeter of mass 60 gram. The final temperature becomes 40 degrees Celsius. Calculate the specific heat of the oil in calorie per gram per degree Celsius. So here a piece of copper of mass 200 degree and specific heat is heated to 100 degrees Celsius and then it was put into 120 gram of oil at 20 degrees Celsius and that oil was contained in a copper calorimeter of mass 60 gram. The final temperature becomes 40 degrees. Final temperature becomes 40 degrees Celsius. Calculate the specific heat of the oil. Like we know that there is principle of calorimeter, which is the heat gained equal to heat lost by the hot body is equal to the heat gained by the cold body or cold substance. So we will use that formula and we will calculate the unknown, that is specific heat of the oil. So I request everyone to solve it and then we will discuss it after a few minutes. Yes, anyone solved it? So we know the heat gained by the oil and the calorimeter is equal to the heat lost by the copper, because copper was heated to a temperature of 100 degrees Celsius. However, the oil was at 20 degrees Celsius and the copper calorimeter is 60 gram. So what will be the now it is given the final temperature is 40 degrees Celsius. We need to calculate the specific heat. Now heat lost equal to heat gained. Heat lost by copper, heat gained by oil plus calorimeter. And the specific heat of the copper is given and specific heat of oil is to be calculated. Now it is MC delta T equals to MC delta T plus for oil plus MC delta T per calorimeter. So mass of copper is 200 grams. So 200 into specific heat of the copper is 0.1. So specific heat of copper is 0.1 and delta T. What is delta T? That is the initial temperature minus final temperature. Now copper was initial temperature of copper was 100 degrees Celsius and the final temperature is 40 degrees Celsius. So it will be 100 minus 40, that is 60 degree. So this is heat lost, and then heat gain. Heat gained will be for oil, there is 120 gram of oil into specific heat of the oil is unknown. Suppose this quantity is S, which we want to calculate, and the temperature difference is 20 because it was 20 and then the initial temperature 20 and the final temperature is 40. So it is 40 minus 20, that is 20 plus heat gained by the calorimeter also. So the calorimeter was again the calorimeter um, for calorimeter, the copper calorimeter, the mass is 60 grams. So it is 60 into specific heat of the copper is 0.1. It is given. And again, the change in temperature is 20 because the temperature also final temperature becomes 40 and the oil and the calorimeter was initially at 20 degrees Celsius. So it is 20. So when you calculate it, it will be 12 into 2400 S plus 120 equal to 1200. So S will be 1080 divided by 2400, which is equal to 0.45. So this is 0.45 calorie per gram into degree Celsius. So it is 0.45 calorie per gram into degree Celsius. Is it clear to all of you? Yes, anyone? So let's solve the next question. The question says two liquids A and B are at temperature 60 degree and 40 degree respectively. Their masses are in the ratio 3:2 and their specific heats are in ratio 4:5. Calculate the final temperature of the mixture of these liquids, ignoring the heat exchanged by the containers. So we will use the same formula, that is heat gained equal to heat lost. So the two liquids were at temperature 60 degree and 40 degree. Here we don't know the final temperature, but we know that their masses are of the ratio 3:2 and their specific heats are in ratio 4:5. So we need to calculate what will be the final temperature of that mixture. And in this process, we will ignore the heat exchanger by the container. So only between the two liquids, we will consider the exchange of heat. So I'll give you a few minutes to try it and then I will solve it. Anyone solved it? So it is given there is two liquids. Suppose the mass of one liquid is X. Suppose this is liquid A, this is liquid B. Their masses are in the ratio of 3:2. So if this is X, then the mass will be 2/3x of B. This is mass and then specific heat. If this is Y, then it will be 5/4y, is not it? Because it is given the ratios are like this. Now, A was a temperature of 60 degrees Celsius, B was a temperature of 40 degrees Celsius. So now heat gained is equal to heat lost. So suppose T is the final temperature of the mixture, then here it will be 60 minus T because 60 will be T will be less than 60 and T will be greater than 40. So in this case, temperature will be T minus 40 degree. So if you solve it, heat lost by A is equals to heat gained by B. So it will be M is X, C is Y or specific heat is Y, XY into delta T is 60 minus T is equals to 2 by 3x into 5 by 4y T minus 40. So xy gets cancelled out. 60 minus T is equal to 10 by 12 T minus 40. So it is 12 into 60 minus T equal to 10 into T minus 40. That is 720 minus 12T is equal to 10T minus 400. So this gives 1120 equal to 22T. So if you solve, T will be 1120 by 22. So it will come around 50.9. So T is 50.9. So the correct option is option C. Is it clear to all of you? Okay, so let's solve the next question. The question says the unit of thermoelectric power is. So we know power is energy per unit time. So thermoelectric power will be thermo EMF for thermoelectric power will be thermo EMF per degree Celsius. So thermoelectric power will be volt per degree Celsius. So thermoelectric power means electric power is volt per time, thermoelectric power is volt per degree Celsius. Then the next question, the question says a 15 ohm resistance is connected in the left gap and an unknown resistance less than 15 ohm is connected in the right gap of the meter bridge. When the resistance are interchanged, the balance point is shifted by 20 centimeter. Then the unknown resistance is. Now this question is based on the carry force bridge operation. So we will uh, apply the we discussed there are different steps to calculate the unknown resistance. So we will calculate what will be the value of the unknown resistance. So here there are two resistances. So if you see here, there are two wires here and here. This is a galvanometer is connected here. So we can see this is the two resistance and this is the case. This is 15 ohm and this is X. So there are 2 points. It is J2 and it is J1. So we will apply the formula and we'll calculate what will be the value of the unknown resistance X. So please try to solve it and then we will discuss.
Sir, is it 8 ohm?
Yes, once again.
Is it 8 ohm?
No, the correct answer is 10 ohm. Because you should keep in mind that the total length of the wire is 1 meter or 100 centimeter. So let's solve it. So now this will be, if you call this is R and this is X, then the relation is R by X equals to L divided by 100 minus L. So when you reverse it, it will be X by R equal to 100 minus L by L. Is not it? But if you see here, it is given that X is less than 15. So in first case, this L, so this since R is greater than X, so this L will be greater than 100 minus L. So it is given when the resistance are interchanged, the balance point is found to sit by 20 centimeters. So the difference between this L and 100 minus L is 20 centimeters. So L and 100 minus L is difference is 20 centimeter, but which is large, which is small. Since X is less than 15, so 100 minus L will be less than L. So since 100 minus L will be less than L, so we know that 20 means 1 will be either, so it will be 100 minus L and this is L. So if you calculate the value, 100 minus L will be equals to L minus 20 because that difference is 20. So L is 60 centimeter. So if you put L here 60, then it will be 60 by 40 and X is less than 15. So R is 15, X is less than 15. So it is 60 and it is 100 minus 60 is equal to 40. So L is 60 centimeter. So when you calculate, it will be how much? 15 by X equal to 60 by 40. So X will be 60 by 6 or X will be 10 ohm. Is it clear to all of you? X will be 10 ohm because if you see, according to the formula, R by X equal to L by 100 minus L. Since R is greater than X, so L will be greater than 100 minus L. And the difference between two is 20. So 100 minus L equal to minus 20. So 100 minus L equal to L minus 20. So from this we calculate L equal to 60. So using L, the value of L in this formula, 15 by X equal to 60 by 40. So X is 10 ohm. Then the next question, Question says the resistance of 4 ohm and 6 ohm are connected across the left gap and the right gap respectively of a meter bridge. When a 2 ohm resistance is connected in series with a 4 ohm resistance of the left gap, the shift in the balance point is. So it is pretty much similar to the previous question. So there are two resistances here, and this is this is 100 centimeter. So one is 4 ohm, another is 6 ohm across the left and right gap. So a meter bridge when 2 ohm resistance is connected in series with the 4 ohm. So in the second case, another 2 ohm resistance is connected here. Then the shift in the balance point is. So initially it will be 4 by 6 will be L by 100 minus L. So L will be here how much? L will be 400 minus 4L equal to 6L. So 10L equal to 400, L equal to 40. So L will be 40 in first case. So, but when we change it, then it will be 6 by 6 because when you add another resistance of 2 ohm in series, then 4 plus 2 equal to 6. Then in second case, it will be 6 by 6, L by 100 minus L. So from here it is clear, it will be 50, L will be 50 in this case. So the shift is how much? Shift is 50 minus 40, that is 10 centimeter. So the shift is 10 centimeter. Is it clear to all of you? Because initially the resistance was 4 ohm and 6 ohm. So the ratio of L divided by 100 minus L will be 4 by 6. But when another 2 ohm resistance is connected in series with 4 ohm, then the equivalent resistance 6 in both sides. So the balance point will be in between 0 to 100. So it will be 50. So initially it was 40 centimeter, but now it is 50 centimeter. So the shift is 10 centimeter in this case. Then next question. The question says the thermo EMF for a given thermocouple is given by E equals to 20T minus 0.05 T square. Assuming that the cold junction is at 0 degrees Celsius, find the neutral and inversion temperature of the thermocouple. So first we need to know what is the final and what is the inversion temperature. So sorry, what is the neutral and the inversion temperature? Neutral, what is neutral temperature? Now temperature at which the thermo EMF is minimum, that is d by dt is equals to 0. And what is inversion temperature? The inversion temperature is where E equals to 0. So the first derivative of E with respect to T equal to 0, then at that temperature, it is at the temperature is called as neutral temperature, and the inversion temperature is where the E is equals to 0. So this is 20T minus 0.05 T square. As I had told you before some time, B is negative, A is positive. So here, as you can see, B is negative. So what is neutral temperature? So for neutral temperature, d by dt equal to 0. Then that temperature is called as neutral temperature. And what is inversion temperature? Inversion temperature is E equal to 0. Then what is T? So if you solve d by dt, then d by dt will be 20 minus 2 into 0.05 t equal to 0. So t will be 20 by 0.1. It is 200. So T is 200 degrees Celsius. This 200 is neutral temperature. And then putting equal to 0 for inversion temperature, it will be 20 minus 0.05 T equal to 0. So T will be 400 degrees Celsius. So this is inversion temperature. So the correct option will be option B, 200 and 400. So the temperature at which thermo EMF is 0 is called as inversion temperature, and the temperature at which the rate of change of thermo EMF with respect to temperature is 0 is called as neutral temperature of the thermocouple. Then the last question of today's session. In previous problem, if the temperature of the cold junction changes to 20 degrees Celsius, then what will be the value of neutral temperature? So if you, so according to, so in the previous question, the cold junction was at 100 degree, the cold junction was at 0 degrees Celsius. So in the question says in previous problem, if the temperature of cold junction changes to 20 degrees Celsius, then what will be the value of neutral temperature? So if you talk about neutral temperature for a particular thermocouple, the neutral temperature always remains constant. So in previous case, the neutral temperature was 200 degrees Celsius. So in this case also, the neutral temperature will not change. So it will remain fixed. It is constant, which is 200 degrees Celsius. So also there is a formula. If you know the neutral temperature of the thermocouple and inversion temperature of the thermocouple, then the temperature of the cold junction you can calculate. Because for thermocouple, the neutral temperature, the formula is theta n equals to theta I plus theta c by 2. So where this is neutral temperature, it is inversion temperature, and this is cold junction temperature. So if you calculate it, it will be theta c will be 2 theta n minus theta I. So this is the relation between neutral temperature of thermocouple, inversion temperature, and cold junction. And also you should remember that the cold junction, so the neutral temperature always remains fixed. So due to dependence of the cold junction, the inversion temperature varies. So here the neutral temperature will be same as that of the previous case, that is 200 degrees Celsius. So these are the problems related to the experiments that we discussed today. In the next class, we will discuss some other experiments covered in that week's lectures. So is there any doubt in today's session questions or any other doubts you have related to the course? So thank you all for joining in today's session. In next session, we will discuss a few more experiments and we'll discuss some problems related to that experiment. So thank you again. That's it. Good night.